In this video, we're going to be talking about the Modern Refrigeration version, edition 20, chapter 4, which is on energy and matter. Now, this can go along with the homework reading or the course material, but this is a pretty important starting point for what we're doing with air conditioning. We're basically converting energy from one form to another and using that energy conversion or the force to move refrigerant around and change pressures and so on and so forth. So the objectives of this chapter is we need to be able to differentiate between matter and energy, need to be able to summarize the relationship between force, work, and power, and need to differentiate between the Fahrenheit, Celsius, Rankine, Kelvin temperature scales. We also want to be able to use the appropriate formulas to calculate enthalpy, specific enthalpy, and changes in heat for a given substance. You want to be able to compare the radiation, convection, and conduction methods of heat transfer. You want to be able to illustrate the differences between the three states of matter. We want to differentiate the sensible heat and latent heat, and you want to predict the effect of a drop in temperature or an increase in pressure on saturated vapor. And you want to be able to explain the relationship between mass, weight, and density. You want to be able to explain the concepts of specific gravity and relative density, and compare the different units used to measure the refrigeration effect. So let's start off with the basic systems of measurement. We have US customary, which is foot for distance and pounds for mass. We also have the System International units, which uses meters for distance and grams for mass. Matter is the building blocks of the universe. The states of the matter could be solid, liquid, and gas, and those are your three states of matter. Energy, so the definitions are the ability to affect change in matter. Energy has a capacity to perform work. The forms of energy, we have potential energy and we have kinetic energy. So there's a law of conservation of energy. This law says that energy cannot be created or destroyed. It's only changed from one form to another. And this is very important. Okay, we don't lose energy just because we take electricity and make it do work with a motor. We're changing it from one form to another. We're changing the electric energy or the voltage potential. We're changing it to a combination of heat and force. But the total energy is not lost. So this is just an example of energy conservation. I have a propane tank, which is chemical energy stored. Then we change it to a flame because we ignite it and make it burn. That's thermal energy. I heat the water, that's steam or thermal energy. I turn the turbine, that's mechanical energy. I turn the belt for the generator using that mechanical energy, that becomes electrical energy. And then I power the light bulb, this becomes light and thermal energy. So again, we're not destroying energy or using energy. We're just converting it from one form to another. Mass is the quantity of material. Okay, so every object has mass. Weight is the gravitational force exerted on the object. As the quantity increases, gravitational force increases. As distances from the Earth increase, in other words, as you get further away from the center of the Earth, the gravitational force decreases. For US measurements, we use ounce, pound, and ton. For SI units, we use grams and kilograms for measurements of weight. Density is the amount of substance within a given amount of space. It's mass per size. So for US measurements, we use pounds per cubic foot. For international measurements, we use kilograms per cubic meter. And that's how you see these both written, pound/foot 3, kilograms per M3. When comparing the densities of gas, it's common to use their specific volumes. The specific volume is the volume of a specific amount of gas under standard conditions. Standard conditions is very important, okay? This is 68 degrees Fahrenheit or 20 degrees Celsius at 14.7 pounds per square inch absolute. That's sea level, or 101.3 kPa, okay? And again, this is sea level, 14.7 psia, air pressure at sea level. Your gauges will show 0, okay? So 68 degrees Fahrenheit, 14.7 psia is standard conditions. So if we take 1 pound, okay, of carbon dioxide at that standard condition, it takes up 8.15 cubic feet. Air, 13.454 cubic feet. Ammonia, 21 cubic feet. Hydrogen, 178.9 cubic feet. That's the volume of the specific gas under standard conditions. And again, we could use 1 pound. Specific gravity is the ratio of a mass of a certain volume of liquid or solid compared to the mass of an equal volume of water. Water has a specific gravity of 1. Objects that float on water have a specific gravity of less than 1. Objects that sink in water have a specific gravity of greater than 1. Okay, so liquid or solid compared to water. Water is the reference material, specific gravity of 1. Relative density is the ratio of the mass of a certain volume of a gas compared to the mass of an equal volume of hydrogen. Okay, so again, we're dealing with our reference material, hydrogen. Again, standard conditions have to apply. 68 degrees Fahrenheit, 14.7 pounds per square inch absolute. At equal temperatures, pressure, and volumes, 2 different gases should have an equal number of molecules. Again, at equal temperatures, pressures, and volumes, 2 different gases should have an equal number of molecules. Force is the energy applied to matter that causes a change in velocity. For US, we use pounds of force, lbf. For standard units, we use newtons. Okay? So if we have 1 pound of a material sitting on Earth, we have 1 pound of force pushing down on the ground. Okay? If we have 1 pound sitting on the moon, which has a much lower gravitational pull, we have 1/6 of a pound of force pushing down. Force, again, it's a straight line to another object or to a wall or to the earth. Work is force multiplied by distance traveled. Okay, again, the amount of work is force times the distance. So for US customary units, we use foot per pound. For standard units, we use joule and newton times meter. So for us, the work formula would be force, which is pounds, times distance, which is feet. Power is the rate at which work is performed. For US units, we're using horsepower. For standard units, we're using watts. So power equals work divided by time. So if we're moving 550 pounds in 1 second, 1 foot up, okay? Power equals work divided by time. So, well, let's talk a little bit about heat, cold, and temperatures. Heat is the energy causing motion in atoms. As temperature increases, atoms move very rapidly. As temperature decreases, atoms slow down. Absolute zero is an absence of all heat. Cold is the result of removing heat. Okay? Cold, result of removing heat. To make things cold, we have to remove heat. That's a pretty important concept. Temperature is a measure of heat intensity. Temperature and heat are not interchangeable. It does not give the amount of heat energy in the substance. Heat energy equals temperature times mass. In other words, we need to know the mass of the substance and the temperature of the substance to calculate heat energy. Temperature scales, we have Fahrenheit, Celsius, Rankine, and Kelvin. Okay? Rankine is based on absolute zero. Okay? 0 degrees Rankine equals negative 460 degrees Fahrenheit. It's absolute zero. Kelvin is based on Celsius absolute zero. 0 degree Kelvin equals negative 273 degrees Celsius. Again, absolute zero. So when we take a look at the different temperature scales, you'll see that Celsius and Kelvin go together. 0 degrees Celsius is 273 degree Kelvin. 32 degree, which is freezing of water, Fahrenheit, is 492 degrees Rankine. Our standard condition for temperature is 68 degrees Fahrenheit, which is 528 Rankine, 293 Kelvin, and 20 Celsius. Boiling of water happens at 212 degrees Fahrenheit, 672 degree Rankine, 373 Kelvin, and 100 degrees Celsius. The ambient temperature is the temperature of air surrounding an object. It's often used in reference to air-cooled condensers, motors, or other components. The ambient temperature will affect system efficiency and sometimes trip safety devices. Ambient may not be constant, especially outside. Your ambient temperature on one side of the unit may be higher than the ambient temperature on another due to sunshine. Rain and snow affect ambient temperature, and wind affects ambient temperature. The greater the wind, the lower the ambient temperature. So ambient temperature is constantly changing, and your thermometer in your truck or car may not equal the ambient temperature anyplace else. So again, it's used in reference to an air-cooled condenser, motor, or other component. Sometimes we use it in reference to the house, okay, but it's always the temperature of air surrounding an object. Specific heat capacity is the amount of heat added or released to change temperature. Okay, in the US, it's based on the amount of heat to change temperature of 1 pound of a substance by 1 degree Fahrenheit. For international units, it's the heat amount added or removed to change temperature of 1 kilogram of the substance by 1 Kelvin. So if we look at the chart over here on the right, okay, we find water down here at the bottom. Water is a pretty important reference substance. That's why I always point out water. And I'm not going to go through the Celsius or the international over here, the charts here. It's also in the book. Okay, but water, it takes 1 pound, no, it takes 1 degree of heat, okay, or 1 BTU to raise or lower 1 pound of water by 1 degree Fahrenheit. Okay, if we take a look at copper, or let's look at glass, it takes 0.187 BTUs to raise or lower the temperature of glass by 1 degree Fahrenheit. Ice, which is just another form of water, it takes 0.504 BTUs to raise or lower 1 pound of ice 1 degree Fahrenheit. Now remember, when you raise ice up to 32 degrees, all of a sudden you're going to go through a point in change where it's going to change from ice to water, and then all of a sudden you're going to have your 1 BTU per pound. Okay, now we introduced another term here. A BTU is a measurement of heat energy. Okay, so let's talk a little bit about BTUs. I have 1 pound of water in a cup. I have a burner with flame. My temperature of the water before I start this is 63 degrees. My temperature of the water after I do this, after I heat it, is 64 degrees. I have added 1 BTU because it takes, water again is our reference substance. It takes 1 BTU to raise the temperature of water 1 degree Fahrenheit. And again, our international units are over here. Enthalpy is the total amount of heat in a substance. It's calculated from a reference temperature. For water and vapor calculations, we use 32 degrees Fahrenheit. For refrigerant calculations, we use negative 40 degrees Fahrenheit. So enthalpy in the formula is H. M is the mass of the substance. C is the specific heat of the substance. And delta T, this is a very frequent measurement you're going to see, is the difference between the measured and the reference temperature. And again, our reference temperatures for water or vapor is 32 degrees. For refrigerant, it's negative 40 degrees. So heat enthalpy equals mass times specific heat times delta T. That is a formula you probably should know. So the specific enthalpy is the enthalpy per unit of mass. It's measured in BTUs per pound or kilojoules per kilogram. We're going to worry about the BTUs per pound right now. So the specific enthalpy is the enthalpy divided by mass. So we have 3 methods of heat transfer. Okay, heat transfer is basically how we move heat from one place to another. We have radiation, we have conduction, and we have convection. Radiation is the heat transferred by heat rays. Heated surfaces lose heat through radiation. Cold surfaces absorb radiated heat. So let's just basically say heat will always move from hot to cold. Okay, the heat transferred by heat rays, heated surfaces lose heat through radiation, cold surfaces absorb radiated heat. Conduction is the flow of heat due to molecular vibrations. Heat insulators conduct heat poorly. That's insulation like in the walls of a building. Convection moves heat by way of a liquid or gas. So let's go back one slide and take a look at the pictures again. Okay, radiation. The tubes in here heat up, become brilliant red, and the heat radiates by infrared rays, okay, from one location to another. You will feel warm standing in front of the heater, but if you move off to the side, you're not going to feel that heat as well. Conduction. We heat up these elements, they start glowing, getting warm, because the molecules in here get excited because of the current flowing through it. Okay, when you put a pan on it, we transfer that heat by the surfaces touching. Convection, we heat the air that the blower is blowing across the coil, and we blow it out the register. That's convection. So one of the final things we really need to talk about is the states of matter. It's the physical state of a substance that depends on temperature, pressure, and heat content. A solid keeps its shape even when not contained. Ice is a solid. Wood is a solid. Liquid has a definite volume but no definite shape. It takes the shape of its container. In other words, without a container, liquid is just going to spread out into a big puddle. Gas has no definite shape or volume. It will always expand to fill its container. Solid, liquid, and gas are my three physical states of matter. Latent heat is heat that causes a change of state with no change in temperature. Evaporation, we take our liquid to gas. Condensation, we take our gas to liquid. You're going to find this throughout the refrigeration cycle. Anytime we do anything with refrigeration, we have both evaporation and condensation. Latent heat of vaporization, latent heat of fusion. Okay, so to boil water off into vapor, it takes 970 BTUs per pound of water. To boil off R22, which is one of our refrigerants, from liquid to vapor, it takes 101 BTUs. To boil off R410A from liquid to vapor, it takes 117 BTUs per pound. Okay? So latent heat is the heat that causes a change in state. I have to add latent heat at the boiling point of a liquid to get it to change to vapor. I have to remove latent heat at the condensation point to get it from a gas to a liquid. We're not even talking about ice here because I do have to do the same thing on the solid to liquid. I have to add latent heat to get it from a solid to liquid. Okay, so when we're talking about the three states of water, we have ice, we have water, and we have steam. So even though the chart doesn't show it, okay, we have 32-degree ice and I can have 32-degree water. The difference is the latent heat. I can have 212-degree water and 212-degree steam. The difference is, have I added or removed that latent heat? Condensation and evaporation, boiling off and condensing. It's part of the refrigeration cycle. Sensible heat is the heat that causes a change in temperatures of a substance. Okay, now here's a enthalpy diagram for water. Okay, let's take a look at this, starting with A. Negative 40-degree water, okay, is ice. We take and we add sensible heat to bring the temperature up to 32 degrees, which is your point B on the chart. We then add latent heat, okay, and now I have 32-degree water. We continue to add sensible heat, and we bring it up to 212-degree water at point D. Then I have to add 970 BTUs per pound of heat energy for my latent heat change, which then at point E, the water becomes steam. So again, I could have 212-degree water as well as 212-degree steam. You can take this for any substance. Okay, we could do the heat diagram for refrigerant as well. We could do the heat diagram for carbon dioxide. This would be, the temperatures would change because every substance has a different boiling and freezing point. But we still have sensible and latent heat that takes place. Again, part of the refrigeration cycle. We are boiling off refrigerant in the evaporator, and we are condensing refrigerant in the condenser. So in the evaporator, I have my liquid, okay, refrigerant coming in, and then at a certain temperature, I've absorbed all the sensible heat, and now I have to absorb a lot of latent heat, and then it becomes a gas and moves on to my compressor. So all the way through, there are heat changes, heat content changes going on through the refrigeration cycle, and we'll get more into that. This is called the refrigeration effect. Okay, a ton of refrigeration is 2,000 pounds times 144 BTUs per pound divided by 24 hour. It's the amount of heat energy absorbed when 1 ton of ice melts in a 24-hour period. So again, a ton of refrigeration is based on ice melting. 2,000 pounds times 144 BTU per pound divided by 24 hours. And the reason we use 144 BTUs is because it takes 144 BTUs to melt 1 pound of ice, from 32 degree ice to 32 degree water. Okay. So my 1 pound of 1 ton of refrigeration is 12,000 BTUs per hour. That's where the ton comes from. A ton of ice times 144 BTU per pound over a 24-hour period. Ice absorbs 12,000 BTUs per hour to melt it to water. So that is everything in the chapter 4 of the Modern Refrigeration book regarding energy. Okay, it's very important. This is a very important concept because all through your career in HVAC, you're going to be talking about temperatures, pressures, temperature-pressure relationships. You're going to use the refrigeration effect. You're going to be dealing with mass and force, and it's all wrapped into one.